This is our Chapter 11 video that has an introduction to intermolecular forces, and we're also going to review VSEPR theory and polarity so that we can get ready to have more conversations about intermolecular forces. When we talk about substances transitioning between solids and liquids and gases, there's multiple ways to cause those kinds of phase changes. Now, the difference that we talked about with solids, liquids, and gases is the space between the particles and how they are interacting with each other. Those interactions are called intermolecular forces, and we call them IMFs for short. We talked about these intermolecular forces when we talked about why gases are so different than solids and liquids. We said that for a solid, the intermolecular forces are stronger than the kinetic energy, which holds the particles in place. But for gases, the kinetic energy is higher compared to the intermolecular forces. And that means that the particles are going to be willing to be very apart from each other, and there's a lot of empty space in a gas. It also tells us something about the movement of the particles. For a solid, the particles can't really move much, they're only going to wiggle. And for gases, the molecules are so far apart and they are moving totally freely, kind of in random motion. Now again, all these properties come down to intermolecular forces. Solids have strong intermolecular forces, and gases have weak intermolecular forces. That means that in a gas, the particles are not very attracted to each other, and in a solid, they are very attracted to each other. Intermolecular forces, which we sometimes abbreviate IMFs, are the forces holding solids and liquids together. They are attractions, and they could also be repulsions. But we are only going to talk about the attractive forces. What they are not is chemical bonds. The type of intermolecular force a substance may exhibit is dependent on a couple things. It's dependent on charge of the substance, it's dependent on the polarity of the substance, and it's also dependent on molar mass. So I thought it might be a good idea for us to discuss and review polarity. Now remember, when we are trying to decide whether something is polar or not, the conversation really starts back at a Lewis structure. And then we use a valence shell electron pair repulsion model. So that's our 3D model to look at where the electrons are in the molecule. And then we look for symmetry with respect to electrons, and we decide if the compound is polar or nonpolar. So what we're going to do is we're going to practice with some of these structures, and we're going to write a Lewis structure, then we're going to make a VSEPR model, and then we're going to decide if the electrons are symmetrical, that's going to be nonpolar, but if the electrons are asymmetrical, that's what we call polar. For carbon dioxide, the Lewis structure would look like this. So I'm following all my rules for making a Lewis dot structure. Everything needs to have an octet. I picked a central atom. I used the number of valence electrons that the carbon and oxygen provided. When I make a VSEPR model of that, it doesn't really change. Around the central atom is still linear. It has a linear molecular geometry. Now when I look at the symmetry, I can cut it in this direction, and I get the same number of electrons over here as I do over here. And I can also cut it in this direction, and I get the same over here as I do over here. So this is a very symmetrical molecule, and it is nonpolar. Now let's do the same for C2H4. it would have a structure like this. And when I make that into a Vesper shape, again, it doesn't really change a whole lot. Around each of these carbons, the shape is trigonal planar. When I'm looking for symmetry with respect to electrons, I can cut it in this direction, and I see the same number of electrons over here as I do on this side. And then if I cut it in this direction, I see the same number of electrons over here as I do over here. So very symmetrical, and we would call that, again, nonpolar. All right, so I'm keeping track of the ones that we've done so far. And now we're on to NH3. For NH3, the Lewis structure looks like this. And its Vesper model gets a little bit more interesting. So this is going to be my lone pair. This is going to be the hydrogen moving out to the side. This is the hydrogen coming towards me, and this is the hydrogen going back into the plane of the page. Now when I look for symmetry around the center atom, and I'm looking for symmetry where we're talking about electrons, if I'm approaching from this direction, I see this lone pair up here, but if I'm approaching from this direction, I don't see any lone pairs. When I have that kind of mismatch, one side is very different from the others from an electron point of view, we mark that in a couple different ways. We can do it in the delta symbol, so a delta negative on the electron-rich side and a delta positive on the electron-poor side. That's the positive side. Or we can draw an arrow towards the negative side, and we put a little positive on the other end. And both of those symbols are trying to tell us that there are more electrons on this side and that there are less electrons on this side. And because there are more electrons on one side than the other, we call that a polar molecule. For water, we get a Lewis structure that looks like this. And for our Vesper structure, we might get something that looks like this. And again, we see a lot of electrons on one side. That's our electron-rich side. We don't see any electrons on the other side, which is our electron-poor side. And we can draw the arrow like this. That means that water is a polar molecule. Okay, for this compound here, we'd have the carbon in the middle, a hydrogen, 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 and a chlorine. Our Vesper model looks something like this. And if we're looking whether something is symmetrical or not, we're going to look at areas of electrons. I can see that this side, the chlorine side, has a lot of electrons. The other side, the hydrogen side, does not have any lone pairs of electrons. And so that means that the chlorine side is what we call electron-rich, and the hydrogen side is electron-poor, and that makes it a polar molecule. Now we've decided that these compounds were polar, and I've kind of written out the Vesper structures again. Now we've decided that these compounds are polar, and I've drawn their Vesper structures again for us over here. When we decided whether compounds were polar or not, we basically just said it is either one or the other. They're nonpolar or polar. But in this chapter, it's going to start mattering how polar something is and which compounds are more polar than others. So eventually, we're going to have to be able to look at these and decide which one is more polar and which one is less polar. And when we need to do that, we'll start looking at some data, and we'll also start looking at how symmetrical the compounds are. We said that all of these were asymmetrical with respect to their electrons, but some of them are more symmetrical and some are less symmetrical. So when we need to start talking about relative strengths of polarity, we'll start looking at some good models and some data to show us what creates a very polar molecule and what molecules are polar but not that polar. Now again, we're interested in polarity because the structure of the particles determines whether it's polar or not, and that determines the strengths of the intermolecular forces that hold those substances together. The intermolecular forces are just attractions that are electrostatic forces. So it's the positive end of one molecule being attracted to the negative end of another molecule. And we are really interested in intermolecular forces because that determines the states of substances, whether they're going to be solids, liquids, or gases. Now, when we talk about intermolecular forces as electrostatic interactions, those are just fancy words for saying that the negative end of one molecule is going to be attracted to the positive end of another molecule. So these are two Lewis structures that represent the hydrochloric acid molecule. And if we look at it, we can see that this is a very electron-rich side, and this is a very electron-poor side. And we can do the same thing for this one. Now, when we say electrostatic interactions, we're talking about the attraction between the negative side of one molecule and the positive side of another molecule. Now, this is a much fancier picture, but again, this is the negative side and this is the positive side. And what this picture is showing us is that the attraction between the negative side of one molecule and the positive side of the other, there's an attraction there, about 20 to 30 kilojoules per mole, but that attraction is very small compared to the attraction between the hydrogens and chlorines in one molecule. The attraction between the hydrogens and chlorines is about 432 kilojoules per mole, so almost 10 times more. So what that's showing us is that the attraction between molecules, which is an intermolecular force, is not the same as a chemical bond. So it is not as strong as the bonds that hold the molecules together. And so down here it says intermolecular forces are much weaker than the bonds that make up compounds. That's why we call them intermolecular forces and not bonds. So the reason why we have intermolecular forces and intermolecular attractions is because there's an attraction between the opposite charges on two molecules. And the most basic way to see this is that the positive end of one polar molecule is attracted to the negative end of another polar molecule. We call those polar forces. But there's actually a bunch of different ways that this can work out between molecules, and that's why we have more than one intermolecular force. In this video, we introduced intermolecular forces. We talked about how they are just electrostatic interactions. That means a positive being attracted to a negative. And we talked about how they are important because intermolecular forces determine the basic properties like physical state, whether something's going to be a solid, a liquid, or a gas. Now, to talk about those electrostatic interactions, we also had to review polarity. And that means we went from Lewis structures to Vesper shapes. And from there, we were able to decide whether something was polar or nonpolar. Now, after this video, a good thing to practice would be to go back over your Vesper and Lewis packets to make sure that you can accurately decide whether something is polar or nonpolar.